You know when you're standing by a quiet lake or maybe watching a river rush by, and you just wonder, what's really going on under the surface? I mean, beyond all the beautiful ripples and reflections, there's a whole hidden world, a complex ecosystem buzzing with life. Well, it turns out there's an entire science dedicated to understanding exactly that.
And that science is called limnology. Now, the name itself is pretty cool. It comes from two Greek words, limne, which means lake, and logos, which means knowledge. So if you translate it literally, it's the knowledge of lakes. But as you're about to see, the field today is so much bigger than just that.
All right, let's dive right in. Here's what we've got on tap for this explainer. First, we'll nail down what this science is really all about. Then we'll meet the pioneers who literally built the field. After that, we'll get into why it's so incredibly important. Then we'll look at how scientists classify all this water, take a quick tour of the major aquatic systems, and finally, we'll give you a brand new lens to see the water all around you.
So first things first, the science of inland waters. What exactly are we talking about here? It's time to move past that simple Greek translation and get into the real modern definition.
Okay, this is the key. Limnology isn't just about, counting fish or measuring how deep the water is. It's actually a branch of ecology. It's all about the interrelationship, how every living thing, from the tiniest algae to the biggest fish, connects with each other and with their physical and chemical world. We're talking about the complete story of life in our inland waters.
So where did all this knowledge come from? Well, this deep understanding didn't just pop up overnight. Let's take a look at the key people who really built this field from the ground up.
The story really kicks off with François-Alphonse Forel. He's the one who coined the term limnology while he was studying Lake Geneva. He called it the oceanography of lakes, which is a pretty epic way to start. But things grew fast. By 1922, scientists were already teaming up, founding the International Society of Limnology. Then came a huge shift in thinking, thanks to Welch. He said the central theme should be biological productivity, not just what's in the water, but how much life that water can actually support. That idea is the foundation for how we manage fisheries today. And finally, Shorbel brought us to our modern view in 1987. We study these waters as complete, interconnected ecosystems. That's the idea that drives pretty much all modern conservation efforts.
Okay, so this brings us to a really critical question. Why does an academic field like this matter so much? Well, the answer connects directly to our survival, from a global scale right down to your kitchen tap.
It all comes down to this. The fresh water we're talking about, the stuff that limnologists study, is our drinking water. It's the water we can actually use. And the two most important words on this slide are readily accessible.
Just take a look at this chart. It's kind of mind-blowing. The overwhelming majority of Earth's water is salt water in the oceans. Can't drink it. Of the fresh water that's left, most of it is locked away in glaciers and ice caps. That tiny sliver right there, that's it. That's all the accessible fresh water in our lakes, rivers, and groundwater that billions of us depend on every single day. It is an incredibly precious resource.
Now, to bring that big global picture right down to a human level, check out these numbers from Sri Lanka. While a lot of people have access to safe water, a huge portion of the rural population still relies on wells. And look at this last number. 15% of the entire population can't easily get to a safe water source. This just shows that managing these inland water systems isn't some abstract problem. It's a daily life-or-death reality for millions of people.
So we know these systems are diverse and super important. But how do scientists even begin to make sense of it all? To study and manage them effectively, you need a way to organize them. So let's look at the framework they use to classify water.
The first big split is all about flow. On one side, you have lentic systems. This is your standing water. Think lakes and ponds, where the movement is mostly driven by wind and temperature. On the other side, you have lotic systems. This is your flowing water, rivers and streams, where gravity is pulling everything in one main direction.
Next up is a really simple one. Where did it come from? Is it natural, formed by things like glaciers or tectonic shifts over thousands of years? Or is it artificial, created by people for a specific reason, like a reservoir to store drinking water or a man-made pond on a farm? And finally, we classify by duration. Is the water body perennial, meaning it's there all year round? Or is it seasonal, only showing up after heavy rains or during the wet season, and then disappearing when things get dry? This makes a huge difference for the kinds of plants and animals that can actually survive there.
Okay, so now that we have our classification toolkit, let's go on a quick tour of the major types of inland water systems.
We'll get to see how these different categories play out in the real world.
First up, the big ones, lakes. They're typically lentic, perennial, and natural. Their water level is this constant balancing act between gains from rain and inflow and losses from outflow and evaporation. And get this for a fun fact, over 60% of all the world's lakes are in Canada. As for the record holders, the Caspian Sea is the biggest by area, and the deepest is Lake Baikal in Siberia, which holds a mind-boggling amount of the world's accessible fresh water all by itself.
So, what's the deal with a lake versus a pond? Is it just about size? Well, as this table shows, there's more to it. Size and depth are part of it for sure, but the really cool difference is evolution. Think of a lake as the first stage of a long story. Over thousands of years, it slowly fills with sediment, gets shallower, and becomes a pond. And that pond will eventually evolve into a wetland. It's a life cycle.
All right, let's get into our flowing or Lotic systems. Streams are usually the smaller ones. They tend to be shallow, fast-moving, with rocky bottoms that tumble the water around and keep it full of oxygen. And rivers? You can think of rivers as basically larger, more mature streams. They're the big highways, collecting water from all their smaller stream tributaries and carrying it toward an ocean or another large body of water.
Next up are wetlands. And honestly, this official definition from the Ramsar Convention just nails it. The key phrase here is transition zone. Wetlands aren't fully land, and they're not fully water. They are this critical, vibrant, and super important bridge between the two. And they can be seasonal or permanent, and they are just buzzing with biodiversity.
And finally, we have estuaries. This is where the river meets the sea, where the action happens. It's the spot where all that fresh water from a river system finally mixes with the salt water from the ocean. This creates a really unique environment with what's called brackish, or slightly salty water. And these zones are some of the most productive ecosystems on the entire planet.
So, we've defined the science, we've met the people who built it, and we've toured all the major systems. Now let's wrap it all up and give you your new lens on water.
Here it is, your Limnology Toolkit. 4 simple steps. Step 1, the definition. Remember, it's the ecosystem science of inland waters. Step 2, the context. It's not just some obscure science, it's vital for our survival. Step 3, classify. You can now look at almost any water body and sort it by flow, origin, and duration. And step 4, explore. Remember that every single one of these systems, from a giant lake to a tiny estuary, is telling its own unique story. So, I'm going to leave you with this question. The next time you walk past a pond, or drive over a river, or stand on the shore of a lake, what are you going to see? Will you see a Lentic or a Lotic system? Will you think about its water budget, where it came from, or that incredibly complex web of life that's thriving just below the surface? What story is that water telling you?